today's webinar. Before we actually get started, I would like to remind everyone that a PDF version of today's presentation is available in the file share pod there in the center of your screen. So with that, my name is Crystal Parteca and I'm the project manager for the Northern Grapes Project. One of my responsibilities is to host this webinar series. Today we're having our 6th webinar in the series and it's going to cover the basics of winery sanitation. Our speaker today is Randy Worobo. Randy is an associate professor in the Department of Food Science at Cornell. His research involves looking for alternative approaches to enhance food safety and quality. His outreach and extension efforts provide expertise to the fruit, vegetable, and beverage industries in New York State, and he is widely regarded as an expert in winery sanitation. I'd like everyone to remember that as a participant in today's webinar, you will not have the ability to speak. If you're having any technical difficulties, please type a note in the chat pod over on the left side of the screen and I will do what I can to help. If you have questions, please type them in the chat pod as well. Randy will take a break midway through the webinar to address some of the questions and we'll have some time at the end as well. And Catherine Mansfield, who is an extension enologist here at Cornell, is online and she's going to help facilitate this whole question and answer process, and she'll be answering some of the more basic questions there in the chat pod. So with that, I think I am going to mute my microphone and turn things over to Randy so he can get started with his presentation. Thank you, Randy, for joining us today.
Okay, thanks, Chrislyn. Can everybody hear me okay? Okay. Today's talk is actually a crash course in cleaning and sanitizing specific for wineries. If you have questions, I'll address as many as I can and as clearly as I can. So to start off with, let's just go over a few things in terms of some of the benefits associated with proper cleaning and sanitizing specific for wineries. A lot of people realize that a lack of a sanitation program actually can result in spoilage incidents with their finished wine, whatever it may be. So it definitely assists in improving the finished product quality. In addition, because of the lack of addressing spoilage concerns throughout the winemaking process, production is a lot easier rather than having to deal with problems. So it's more focused on prevention rather than dealing with the problems as they crop up. In addition, because cleaning and sanitizing rely on chemical compounds, the improper use can actually result in dangerous levels of these cleaning and sanitizing agents getting into the finished product, and there have been incidents with this occurring. There's no denying there are costs associated with sanitation, the cost of chemicals, the man hours associated with it, but at the same time, there are definitely costs associated with not doing it properly or not doing it at all in terms of poor product quality to the point where it's unsaleable. Where we have to start off, it's going to seem, it may be very basic for some of you, but it's very important. There's a difference between cleaning and sanitizing. Cleaning is actually removing the soil and debris, any organic matter from the surface, whether it be the contact surface that the wine comes in contact with, but it can also be associated with the harvesting equipment out in the viticulture. If you don't remove this organic material, the problem is that your sanitizers that you apply or your sanitizing treatments that you apply after the effectiveness is dramatically reduced. So the first thing, probably the best way to describe it is you cannot sanitize a dirty surface. So the majority of your focus should be on cleaning to make sure that the surface has got most of the debris removed. And what it does then allows for the sanitizer to easily inactivate any microorganisms that might be left behind after the cleaning process. Now, the difference between cleaning and sanitizing is that the cleaning should do the majority of the work that's where your efforts should be directed. By eliminating that dirt, it allows for the sanitizer to do its effectiveness that it's prescribed to do. Anytime that you don't have that, anytime that you have incomplete cleaning, the sanitizer's effectiveness is compromised. Um, Sanitizing, if you don't have the dirt removed by itself, the majority of your sanitizer is going to be bound up by that organic material and any contaminants that are embedded or even hidden by the organic material or dirt. The sanitizers won't be able to reach it because it's being bound up um, by that organic material. Now, there's actually the proper cleaning and sanitizing for any contact surface. It's actually a 5-step procedure. The first thing that you want to do is pre-rinse, whether it be a tank, any kind of paddles, anything that comes in contact. You want to pre-rinse it simply because this is going to eliminate the majority of the debris, organics, anything that's going to be bound up by your sanitizer. It's not tightly bound, so by pre-rinsing, you reduce the amount of detergent that's required to that's next applied to lift off the organic material that's more tightly bound to the surface. You then want to apply a rinse after your detergent because detergents are normally alkaline in nature, and the majority of the sanitizers are acid in nature. If you don't do that rinse, the pH is going to be equilibrated and it's going to lower the effectiveness of the sanitizer. After you've rinsed off that detergent and the organic matter that's been lifted off by the detergent, then you apply your sanitizer at the prescribed concentration for the prescribed contact time, and it's best to use the manufacturer's recommendations. After that, you then apply an optional potable water rinse. Depending on the concentration and the type of sanitizer you're using, the final rinse may not be necessary. If you're going to be if it's going to be a long period of time between the use of the equipment, a very common industry practice is to do the 5-step cleaning and sanitizing process, and then the next time you use it, you can just do a quick sanitation, so you're able to skip the pre-rinse, the detergent. You can directly apply your sanitizer, leave it for the contact time, and then rinse it off before you actually use it. Now, if you follow the 5-step procedure and do a good job of your cleaning and sanitizing, you dramatically reduce your incidence for having spoilage microorganisms. It prevents biofilms. Biofilms are very, very common if you don't have any type of cleaning and sanitizing regime in place. Biofilms occur, they basically take the nutrients from the wine or from the juice, they use it as a nutrient, and they produce polysaccharides, and it usually occurs on T junctions, any kind of surface where it hasn't been properly cleaned, and it's a form of microbial concrete. The thing is once the biofilm is started, it's now produced an irregular or a pitted surface that allows for crevices for microorganisms to adhere to, and they basically suck the nutrients from the wine or the juice as it passes, and it continues to develop and problem. Biofilms can become so problematic that you actually need ultrasound to remove it from the surfaces, and ultrasound removal is actually quite expensive, and it's sometimes cheaper to actually buy a new piece of equipment rather than trying to remove the biofilm. The other benefit that's associated with a good cleaning and sanitizing program is that because you're doing it on a regular basis, you don't have the type of buildup of biofilms or even debris on the surfaces because you've been regularly cleaning and sanitizing. So it takes less of your cleaning and sanitizing chemicals to get to the point where you want to target. At the same time, everybody makes mistakes, everybody forgets. But if you've been doing a good job of cleaning and sanitizing, you're not going to have the microflora there at the same level as if you had a poor or no cleaning and sanitizing program in place. So it's a lot more forgiving of mistakes when they do actually occur. I've already went over, so with poor sanitation, it can directly affect product quality to the point where it's an unsaleable product. There are some spoilage yeasts, if they're allowed to grow, produce very high levels of off flavors where you can't even blend it off. And the consumers are very fickle in terms of a bad bottle of wine. They automatically associate with the brand name, and their likelihood of going back to your product, especially if it's a faulted wine, is less likely. Excuse me. In terms of where these microorganisms come from, microorganisms are everywhere. Um, One of the most common misnomers is that microorganisms actually seek out and look for the sources of nutrients, being the wine. The thing is that microorganisms have no practical means of locomotion, and its the most common source is the workers serve as the vector to spread the microorganisms from, say, the drain onto the floor, from the floor onto the contact surface, and it gets into the wine. What this slide shows is the various entry routes for microorganisms to get into wine. Under rodents and pests, probably the most common would be fruit flies. Fruit flies can become very big problems, especially in drains. By eliminating wines from the environment, so avoid having standing wines on the floor, so washing it down the drain as quickly as possible, and then flushing your drains on a regular basis. You eliminate the nutrient source for fruit flies, and inadvertently you eliminate one of the entry points for microorganisms. You can also, as I said, humans, the workers are the most common vector for supplying the route of contamination for microorganisms into the wine. One of the most common overlooked entry points that winemakers make is the use of wine thieves. They sample from barrel to barrel without a sanitation of the wine thief between barrels. Unfortunately, if the first barrel that they sample is contaminated with Brett or uh, any other type of Acetobacter, any type of spoilage microorganism, by not sanitizing and you go to the second barrel, you serve as the person that's inoculating that next barrel, and the second barrel could actually not be contaminated, but by the contaminated wine thief, even the residual amount of wine that's in the wine thief when you're taking up the sample is sufficient amounts to cause contamination. One of the best methods for decontaminating wine thieves is you can either have 70% alcohol, you can have a what I usually recommend is a small thermos um, that is filled with hot water. You just have a small heating kettle in wherever your barrel room is. You heat up the water, pour it into the thermos. As long as that water is above 185, you immerse the wine thief into the thermos. It's instantaneous in terms of inactivating all the spoilage organisms associated with wine. So it's very, very quick. So what happens when contamination actually occurs in the wine? Well, obviously they're using the wine as a nutrient source, so they increase in number. Some of the off flavors and off odors that are associated with wild yeast growth are 4-vinyl guaiacol, 4-ethyl guaiacol, phenol, syringol. You can also have hydrogen sulfide, acetic acid, and mercaptans. More associated with wine spoilage bacteria, you can have acids, diacetyl, bitterness, and biogenic amines. So these are the whole gambit of possible defects that might be associated with your finished product. What determines a spoilage microorganism's likeliness of occurring? It's based on extrinsic as well as intrinsic factors. Extrinsic is the temperature that you hold the wine, how much oxygen is there. Carbon dioxide present can also be a deterrent, especially for Acetobacter. Acetobacter are strict aerobes, so if you eliminate the oxygen, you're going to be eliminating the potential for Acetobacter to grow. At the same time, you have the intrinsic factors of the wine itself. available nutrients. So a lot of the spoilage yeast that are associated with wine spoilage, they're they're very good at utilizing any waste or byproducts of Saccharomyces. They can also use the lees left over from fermentation as a nutrient source. Alcohol content, spoilage yeast generally don't grow above 16%, so making the wine is more susceptible at lower alcohol percentages, as well as at the lower alcohol percentages you can have Zygosaccharomyces and even Saccharomyces yeast in a sweet wine causing spoilage. pH and sulfur dioxide are closely related. Always making sure that you have free sulfur dioxide or molecular SO2 in your wine is extremely important, because your your spoilage yeast as well as your spoilage bacteria associated with wine are extremely sensitive to sulfur dioxide. Fortunately, when you compare wine microbiology to other foods, wine is actually it's a form of preservation from juice. So you eliminate a lot of the spoilage microorganisms compared to juice itself. And compared to other foods, wine has relatively few spoilage microorganisms. Food, if you think of any other type, sandwich meats, breads, anything, you can literally have thousands of different types of spoilage microorganisms, and you can have heat resistant ones, you can have molds. Fortunately, all of the microorganisms that are associated with wine are not that resistant, and all of them are heat sensitive. And this is actually why with a filler bowl, the most common practice to sanitize a filler bowl is using heat. At the same time, the finished product of wine it's high value product, so there should be more available resources to dedicate to cleaning and sanitizing as well. But the unfortunate thing with the finished product is that it's highly scrutinized by its consumers. So very few people look at a wine and say how wonderful. They're automatically looking for flavor defects. So there's an expected quality in terms of the flavors, lack of flavor defects, and then also visual characteristics, because any type of spoilage can actually result in a turbid or cloudy product, which is going to be immediately recognized by the consumers. How we actually control the spoilage microorganisms, we can do it through physical treatments or chemical. Physical includes filtration. Typically in the wine industry, 0.45 microns is considered sterile. However, 0.45 is insufficient to actually filter out acetobacter, and then for some stressed wild yeast as well, they form much smaller cells, and they're able to get through the 0.45 microns. At the same time, another physical treatment is thermal or heating. However, there are specific issues that are associated with hot water sanitation, or which may include steam. The generation of hot water is expensive. The generation of steam is expensive, and it also requires dedicated equipment. This is why chemical disinfection methods are more common in the food and beverage and wine industry. And here's just a list of the most common chemical treatments. Chlorinated compounds were widely used in the wine industry 10 years and longer ago, simply because it's broad spectrum, it's very effective, and it's cheap. However, the use of chlorine can result in the formation of trichloroanisols in the finished wine, and it's been so because of this, chlorine has been avoided. There's a paranoia associated with any kind of chlorinated compounds in the winery. Associated with chlorine, you can have iodine or even brominated sanitizers, and it's been speculated that because they're similar to the chlorine compounds, they can actually participate in the formation of anisole compounds, which are also flavor defects in the wine. Quats or quaternary ammonium compounds. These are commonly used. The biggest drawback of quats is that they're relatively ineffective against a lot of the wine spoilage bacteria. It also takes an extremely long time for the inactivation to actually occur. You're looking at hours of contact time versus minutes, which is more common with peracetic acid or hydrogen peroxide or your chlorinated compounds. The peracetic acid, hydrogen peroxide, it's also called peroxyacetic acid. This is increasing popularity for use in the wine industry. Um, it, there are some hazards associated with it. It's extremely caustic, but it does show relatively good effectiveness against wild yeast. At the same time, caustic soda, even though it's used in the wine industry to remove the majority of the buildup, which are tartrates, at high enough concentrations above pH 11, it does strip the membrane of yeast and bacteria and causes an activation of those spoilage microorganisms. Now, sanitation and cleaning aren't the only focus of sanitary operations, but it's also, you have to make sure that all the equipment and utensils are actually clean and sanitized. A lot of people forget that paddles, wine thieves, um, even the backside of valves have to be properly cleaned and sanitized. At the same time, you want to make sure that all your cleaning and sanitizing agents are properly labeled and properly stored. Last thing you want is to have the inadvertent use of a sanitizer or cleaning compound in your finished wine, and this can happen simply because it's not labeled properly. The cleaning and sanitizing chemicals should also be used at the prescribed levels. Pest control, specifically, it's fruit flies in wineries. This can actually be prevented or controlled simply because of the frequency of your waste removal, and the location of your dumpster that you put your pumice in, or the pressed grapes. Um, the hatch time for fruit flies is 3 days. So if you remove your press cake from the dumpster on a frequency of 3 days or more often, you're not going to have the hatching of the fruit flies. Um, Also, by removing it, moving it away from your actual winemaking facility, reduces the amount of fruit flies that actually can enter or gain entry into the facility itself. Now we're going to go on to the cleaning aspect. Um, Cleaning, like I said before, is removing all your dirt, debris, which is primarily organic matter, from your equipment, from the food contact surfaces, anything that comes in contact with the juice of the wine. And it can be usually performed through physical force, which is scrubbing, which may also be high pressure washing, as well as detergents. Detergents are sometimes necessary if there's buildup, because it serves as a surfactant. And what a surfactant does is a wetting agent. It it wets it has a hydrophobic and a hydrophilic group, so it attaches to the water and it attaches to the dirt and allows it to be removed easier than just with water alone. You can have two different types of cleaners. You can have acid or alkali cleaners. Since in the wineries, most of your organic matter is going to be tartrates. Alkali is great for removing tartrates, solubilizes them very efficiently. At the same time, on stainless steel surfaces, it may appear to be clean, but you notice it's got a rainbow sheen. More commonly, it's like a purple sheen on your stainless steel and it doesn't sparkle. This is usually associated with mineral deposits from the water. And by rotating between an alkali and an acid cleaner, you'll get rid of those mineral deposits. I would suggest using alkali 4 out of the 5 days for a facility, or 4 out of 5 cleanings should be alkali, and then that 1 out of 5 can be an acid cleaner, which will remove the deposits that are not lifted off by normal alkali treatments. Now, some examples, these are, I'm not promoting any one company. Um, it's just that I get many questions asking for actual names of detergents. So examples for acid detergents is Apex acid detergent. It's from ZEP. An example of alkali cleaner is Apex process cleaner. In California, water conservation is extremely important, and so and it's becoming more important across the U.S. So biodegradable options include ESP, which is supplied by ZEP. It's for heavy duty. It's non-phosphate and it's non-butylated. So this would be when you have extremely heavy buildups. Then for less heavy buildups of organic matter, for general purpose, GreenLink, it's biodegradable, it's non-chlorinated, it works well. At the same time, for stains that are more common on concrete floors, Z-Green works very well. It's a peroxide based and it strips off the color and stains that are associated with the winemaking process. Now, at the same time, you can have what are called cleaner sanitizers. As you have the detergent that lifts off the dirt, you have in combination a sanitizer that, as it's lifted off, it kills off any microorganisms that are associated with the dirt. This, it has, it's the combination of a cleaner and a sanitizer together. And what this does is it prevents any contamination from being spread anywhere else, because as you're lifting off the dirt, you're lifting off the microorganisms, and it could be spread to other parts of the winemaking equipment. However, a lot of people think that you can go from a 5-step procedure down to a 3-step by having a cleaner sanitizer. You still have to do a sanitizing step after. This is just an added protection step that some winemakers and some of the people in the food industry prefer. Some examples are ZEP Natural or PDC Plain. Now, I'm going to stress it again, and my talk should actually be a cleaning, winery cleaning with less emphasis on sanitation, because you really have to direct your efforts to cleaning. The reason is that without proper cleaning, you don't get an effective sanitation. So if you do a proper cleaning, it it requires less of the sanitizer in terms of performance expectations. At the same time, your effectiveness of your sanitizer is directly affected by reducing the amount of organic binding, because anytime that you have organic material, I said this before, the sanitizer will preferentially bind to that, and it's just like your SO2, where it's bound by organic material and it's no longer effective. So you have the result of this is that you have an overall savings through, it's going to require less of your sanitizer to actually do the job that you're targeting, because you're actually binding up less due to the binding of organic materials. Now you have various different cleaning options. These include manual, which is elbow grease and scrubbing brushes. You can also do soaking, which is great for disassembling pipes, T-junctions, any types of your filler heads, and you soak them in your detergent solution. Normally there's going to be some associated scrubbing with this. There are also some very important things that you want to take into consideration is have correct brushes. So for long pieces of stainless steel piping, you can have very long brushes that need to get in. You need to have you need to guarantee adequate scrubbing at all locations. There are spray methods. This is where you can apply it through a pressurized vessel. It's not high pressure cleaning. You basically apply it. It allows for the detergent to come into contact with the dirt and then lift it off. Um, there's cleaning in place. This is more common in larger facilities. This is where you have a closed loop system and you have a very high volume flow rate of the fluids going through with the cleaner or a detergent in the line. And this basically replaces the scrubbing action that's supplied by elbow grease. You have cleaning out of place, which is it's usually a vibrating table that provides the agitation with the detergent. You have foams and gels. Now, the reason for foams and gels represents a direct correlation to contact time. If you were to spray water, foam, and gel against the wall, you're going to notice that the water streams down the fastest, and then the foam streams down the next fastest, and gel goes much slower. What that correlates to is the amount of contact time that the detergent has directly with the dirt. So if you want a long contact time, gels are the best. You can also use high pressure cleaning. This this is very common for barrels, for floors, for tanks. The issue is you want to be aware that if you're using high pressure, that you're not introducing contamination from where you're doing the pressure cleaning. Be very cautious when you're pressure treating or using high pressure to clean out your drains, because you can actually be providing a vector, spreading the contamination throughout the facility. Okay, I've got some questions specifically. Um, One question was, can ozone destroy biofilm? Ozone will destroy, it'll inactivate the microorganisms, but it does nothing to the biofilm itself. And once you have the biofilm there, it provides an easy substrate for the microorganisms that come in subsequently, and it attaches very quickly. Another question we've got is about, since hoses are typically cleaned by circulation only, are biofilms a particular problem in them? And is it prudent necessary to replace hoses periodically? Or does using foam ball to scrub them out work? Hoses are it depends on the hose. The rubber hoses that are most commonly used for transferring, those are rubber with it's a fiber rubber blend, and those are extremely difficult to clean. Some people will actually boil their hoses, and within the first day they've already got very high levels. Swabbing of rubber hoses that have been treated with citric SO2, um, it swabbing results show that it does not improve the sanitation. They're very difficult to treat. One of the better suggestions to use is Tygon corrugated hoses. They're not as flexible. They're a little bit more expensive, but they're actually opaque, so you can see if there's standing wine, and you can also see how good of a job your cleaner is doing. Next question: what's best point to use ozone? And I currently use it as a final rinse in all equipment. We are also using ozone gas in our oak barrels. Okay, with ozone, if it's dissolved in water, the half-life is extremely short. We're talking seconds. So you have to have a continuous generation of ozonated water. If you have if you have a hose more than 50 feet, at the end of your, by the time it reaches the end of your hose, the majority of your ozone is going to be gone, and you're not going to be getting much of a sanitation kill. Ozone gas has a half-life of about 24 hours. It's going to be much better than the solubilized ozone compared to the ozone than the ozone in water. What Another question: what concentrate of KMB and potassium metabisulfite and citric acid is used for sanitizing? 150 parts per million. Having your pH of, you need to acidify the pH of that to definitely below 3.5. Near 3 is even better, because of the equilibrium, you're going to get more of the free molecular form down near 3. Any other? I gotta scroll up here to see what other questions. Um, okay, other questions. Any other questions before? Okay, we'll move on to the next part. Now, what we're gonna do is, so 10 years ago, when everybody became paranoid about TCA, everybody was saying, "What can we do? What can we do to use as an option for a sanitizer?" The thing is that traditionally chlorine was used in excessive levels, and it actually served as it solubilized the not only the tartrates but any kind of protein buildup that was actually um, on that might be deposited on the surfaces. The thing is that the most important thing to look at is by doing a good job of cleaning. Your sanitizer choice is not as important. Um, Heat is one of the best options in terms of inactivating your typical wine spoilage microorganisms. If you target anywhere between 170 to 185, it's going to be, especially at 185, it's instantaneous for every wine spoilage microorganism. Um, at the same time, in terms of water consumption or water usage, because there are no heat resistant microorganisms associated with the wine spoilage microflora, you can take that water that you used and you can reheat it, and you can use it to heat and activate any other barrels without having any risk of having contamination issues by reusing it. In terms of chemicals, chlorinated compounds, you have TCA issues. How it actually kills is it takes the amino acids and it oxidizes them. And you have different forms of hypochlorites. Um, you have hypochlorites, which is sodium or calcium hypochlorite. This is your household bleach, which is typically 3 to 5% sodium hypochlorite. Your pool bleach is more calcium hypochlorite. This is usually about 60% hypochlorite, so it's a much higher concentration. Chlorine dioxide is very commonly used in the dairy industry and a lot of the other food industries. It does not participate in the production of TCA, so it's its use is increasing in the wine industry because it doesn't have that negative defect associated with it. You also have acidified chlorines because hypochlorite or chlorites are the same as sulfur dioxide. It's a pH dependent equilibrium in terms of having the germicidal species. With any time, if you're using chlorine, you have to have the pH below 7, otherwise you have absolutely none of the germicidal form being formed. Uh, Acidified chlorines, when you mix up your chlorine, you normally have to acidify it. Acidified chlorines have a built-in buffer system so that it automatically drops the pH to below 7 though. Your target concentration is typically about 200 parts per million that you want to target, and you want to do free chlorine, which is the same as molecular form of SO2. Iodine-based compounds, they just stop protein synthesis, and once the microorganisms can't synthesize protein, they die. Typically, the concentration is about 25 parts per million of titratable iodine. It's the same as chlorine and sulfur dioxide in terms of pH optimum, but with iodine you have to be at a much lower pH. Once you at 3.5, there's very little of the germicidal form being formed. You want to really target around pH 2.5. Iodine, like chlorinated compounds and brominated compounds, are extremely sensitive to organic matter. As soon as you have any organic matter there, which means your dirt, it's going to be bound up preferentially, and once it's bound, it does not have germicidal activity. Quaternary ammonium compounds, they're quats or QACs. They just punch holes into the membrane of the yeast and bacteria. For sanitizing, they typically the typical concentration is target about 200 parts per million. For foot baths that may be at the entrances onto the wine production floor, you may be going as high as 1,200 parts per million. Um, and and there are some variations in terms of recommended concentrations. It's usually suggested that you follow the manufacturer's recommendations. You have acid ionic combinations. These are peracetic acid. I would highly recommend if you're going to use a peracetic acid as a sanitizer, use the one that has the hydrogen peroxide in combination, simply because there's a synergistic effect between the peracetic acid and hydrogen peroxide. So instead of getting, say, 99.9% kill with peracetic acid by itself, and you with the combination you actually get 99.9999%. So it's much better because they have two different modes of action. For acid ionic, it targets the cell membrane. It's good against wild yeast, specifically Brettanomyces, and usually the target concentration is about 125 to 250 parts per million. If you go down to 80 parts per million, you don't have to do a potable water rinse after. For hydrogen peroxide, it's a very strong oxidizer, as with peracetic acid. So if you want to avoid spillage for whoever's handling it, because it will cause your skin to oxidize and it'll burn. Your concentration, you're allowed to go up to 1,100 parts per million final concentration. The nice thing about peroxide or with the peroxyacetic acids, they break down to water, oxygen. If you have the peracetic acid combination, it'll break down to acetic acid. So you don't have the residuals associated with this particular sanitizer. For ozone, it's a very it also oxidizes. Unfortunately, it's not a targeted oxidation. It's a hyper radical of oxygen. It wants to get rid of that extra energy, and it basically deposits on everything. Fortunately, when it deposits that extra energy on the microorganisms, it oxidizes it. It has broad germicidal activity, but the problem with it is it has very short half-life, and it's also temperature sensitive. So for the question with ozonated water, what you have to keep in mind is that you have to be measuring the temperature of your water. You shouldn't go much above 70 to 80 degrees Fahrenheit, because the amount of soluble ozone in that water is much reduced compared to colder water, say down around 50 degrees. Now, as with all good things, there's a negative side, and I'm going to go through some of the faults. Despite heat being working extremely well against all microorganisms associated with wine spoilage, if you don't do a good job of cleaning before, you basically bake on any dirt or debris that might be on the surfaces. And once it's baked on, it's like in your oven trying to scrape off anything that's dripped over during baking, and it's bound there, so it causes caking. At the same time, if you're using hot water to sanitize your barrels, you do lose some of your flavors as well as your volatiles just because of the hot water. There's also the energy costs associated with generating the hot water. With chlorine or chlorinated compounds, like I said, you've got the TCA or trichloroanisole byproducts that can be formed. You want to keep in mind that you should be measuring the pH if you are using a chlorinated compound, and then you want to minimize the amount of organic matter, meaning you do a good job of cleaning. For iodine compounds, it stains. If you have any kind of plastic, it's going to stain them brown. It's just a aesthetic thing. It doesn't leach out. It's reactive with starch, and it's not broad spectrum. Especially against acetobacter and lactic acid bacteria, they thrive in iodine-based sanitizers. Quaternary ammonium compounds, I really don't recommend these except for walls, or if you're not going to be using the piece of equipment until, say, the next season. You can apply it. It doesn't cause any pitting on the equipment. But if you use it as your general sanitizer in your facility, you're going to have very quickly a buildup of resistant microflora. Acid ionic, it's narrow spectrum, but fortunately, it's active against the wild yeast that most winemakers want to target. It's reactive with organic, so you have to keep in mind that there's a lot of wood in wineries, and you want to, if you take some of the concentrated peroxyacetic acid and you spill it onto the organic, it can actually spontaneously combust. Hydrogen peroxide, you have oxidizing residues. It's unstable, so as soon as you expose it to the light, it's going to be inactivated. It also readily reacts with SO2, so you have to beware if you're using peroxyacetic acid as a barrel treatment. You may have your free or your molecular SO2 might actually be lowered if you have any residuals that have leached into the barrel. For ozone, dedicated equipment's needed. There's worker hazard as soon as you generate ozone, and it's less effective against spores and wild yeast. For UV, I just tell people to avoid it simply because anytime you have any shadowing, so even on a barrel surface, you're going to have, anytime that the UV doesn't have direct exposure to it, it's not going to have any effect. So specific problems for wineries compared to the rest of the food and beverage industry, you have wood. It's a porous material, as well as it's not sterile when you start it. So the first time you use a barrel, you can have wild yeast associated with a brand new barrel. You have long resident times of the finished product in vats or barrels. It means it has more time for the microorganisms to grow. The biggest thing for wineries is that the majority of the sanitizers and detergents have been targeted to other areas of the food and beverage industry, and wineries are unique in terms of the type of buildup, where it's primarily tartrates, and their spoilage microorganisms are very different compared to all the other food industries as well. So this is a big issue, and this is why there is no one silver bullet to kill all the microorganisms, with the exception of heat. The other thing, this misconceptions or unsubstantiated claims of sanitizers. You have to remember that the chemical supply companies work on commission. So ask for the research that actually shows the effectiveness against whether it be Brettanomyces or against Acetobacter. The other thing is that cleaning and sanitizing hasn't always been a priority for winemakers until you have an issue. And most commonly you see Brettanomyces starting out as a little bit of a problem, and it provides a bit of terroir, but unfortunately, if there's no control, it spreads and becomes out of control. Drains, it's important to make sure that they're flushed regularly to prevent buildup. Probably the best way to flush a drain is to plug up your drain hole, fill it up with sanitized water or even hot water, and then release it all at once, so it guarantees all the surface of the drain gets exposed. For filters, some people like to reuse them. I suggest not reusing them, but if you do a caustic acid treatment and then do a heat treatment to sanitize the filter, and then it's good as a good practice pre-sanitize just with citric SO2 prior to use. For bottling lines, cleaning in place works very well. High pressure to remove any kind of buildup and flushing. You should target heating the external filler bowl using hot water or steam up to 180 to 185. Once you reach that, everything is considered sanitized. You should use, they're called thermal dots. There's adhesive dots that are temperature indicators, and that's a good way, and you put it on the outside of the filler bowl, and it basically means that everything on the inside has been sanitized as well. Rubber gaskets on filler heads, the plastic actually wears out with time, especially if you're using ozone to flush your system. It eats up the rubber, and as soon as you get cracks and crevices, it provides an entry point for microorganisms to get into your finished product. Mobile bottling lines, you want to make sure that they have a good sanitizing and cleaning regime in place before you put your finished wine through. We've already talked about transfer hoses, and for ball valves, butterfly valves are much better and easier to sanitize. Ball valves, because there's always one side of the ball valve that's going to be hidden from cleaning and sanitizing. Ball valves can actually have higher counts compared to drains. Some common faults are inadequate cleaning to get rid of your organic material, not using the right sanitizer, not using it at the correct concentration, or not leaving it on long enough. Recontamination. So as soon as you spend the time to clean and sanitize your equipment, you should prevent it from getting recontaminated. So don't put it back on the floor. Have hooks or a placement system for it. Correctly prepare cleaning and sanitizing solutions using accurate measuring devices, and you should be checking those solutions to make sure that they're properly prepared. There's test strips for all sanitizers. Make sure that you record the information so that you can go back to see if there was a specific issue. And then instead of using one type of detergent, like I said, majority of the time use an alkali, switch to an acid cleaner to get rid of the mineral deposits. At the same time, your sanitizer should be switched at least once a week to once every 2 weeks. Go from a broad spectrum to a totally different sanitizer just to wipe out any type of buildup. So here's an example. Because you've got tartrates as a primary organic buildup, use a caustic detergent days 1 through 4 and a peroxyacetic acid as your sanitizer. On day 5, switch to the acid cleaner to get rid of the mineral deposits, and then a quat because you're going to have days 6 and 7 for it to actually activate. Simple as it is, this is just an example of how to properly prepare a sanitizing solution. Make sure that you measure the gallons of water that you use and how many ounces, and that you've actually got the correct sanitizer, and then measuring the final concentration. How to actually determine whether you're doing a good job of cleaning and sanitizing. You can use traditional microbiological plating, but it's also what's faster is what's called ATP bioluminescence. It's a swab system. What it does is it relies on the firefly enzyme. It picks up any ATP which is associated with any microorganisms that are still alive. You swab it, it reacts with what's called luciferin, and it produces light, and it gives you a rapid indication. We've done surveys of wines. This is for drains, floors, bottling lines, clean what the winemakers considered clean stainless steel tanks, and then around the bunghole of full barrels for 8 wineries. And you can see, as expected, the drains are dirty, the floors are dirty. For the most part, the bottling lines and the stainless steel tanks were also very clean, but unfortunately, right around the bunghole, you can see on wineries 4, 5, 6, and 7, they had counts that were very close to the drain levels, and some were even actually higher. The issue is that they had spillage, and as soon as you have spillage onto the exterior, the free SO2 is bound up by the barrel, and then you've got nutrients there, and the spoilage microorganisms were growing very quickly. It's a good practice just to spray down around the bunghole with 70% alcohol or citric SO2 solution prior to going in to top up or take out with a wine thief. The next slide just shows you the separation of the drain, floor, full barrel, around the bunghole, the bottling line, and a clean stainless steel tank. So in general, everybody was doing a good job of cleaning and sanitizing tanks because they're easily cleaned and sanitized. And then the bottling line, there were very low counts because everybody was using a hot temperature. These are just an example these are the 2 largest sanitizer chemical supply companies. They have offices all across the U.S. They're very, very open to discussing with you. They'll come in, take a look at the type of needs that you have specific to your facility. With that, we've got time for a few more questions. My understanding is that SO2 and chlorine levels much higher than 200 ppm can pit stainless steel. Is this so? Yes, that is, you don't want, that's why the contact time is very important. The higher the concentration, the shorter the contact time, and it prevents the pitting. Next question is there a temperature and duration required to create a sterile environment, or does it just have to reach 185 degrees Fahrenheit? Excuse me. For wine spoilage, 185 will eliminate all the wine spoilage bacteria and yeast. It does not create what microbiologists consider as sterile. You actually have to have it under 20 psi at 220 degrees Fahrenheit. So it's what we would call commercially sterile, but not sterile from a microbiologist point. Next question: is it possible that the air supply to a bottling room can be an important source of microbes? So, should all bottling rooms have a scrubbed air supply? I've seen bottling rooms that have the drain that runs through the center of it. I would not recommend having that scenario. Um, the air doesn't have to be scrubbed. It depends on the air circulation patterns. If you have a positive pressure, so a higher pressure coming into your bottling room, and it basically forces everything out rather than having a negative pressure, is a much better scenario. If you do want to have a sterile air supply coming in, you can have a HEPA filter for the air delivery system just into the bottling room. But a positive air pressure is going to be just as important, because it's not going to be bringing all the potential spoilage of microorganisms from the wine environment. Next question: what's the lethal temperature for Brettanomyces? If you hit 185, it's instantaneous. 165 degrees for 10 seconds will inactivate more than 99.999% of Brettanomyces. Next question: sounds like pH is important for sanitizers. Do you think it's essential that wineries are able to measure pH to do a good job of sanitizing? If you're using a sanitizer that you have to acidify yourself, yes, pH is extremely important, and you should be measuring it with an accurate pH meter. You can also buy sanitizers that have the buffers built into it. If you don't want to deal with the hassles associated with it, so a buffered sanitizing solution is also a possibility. Next question: is steam recommended for bottling lines? You can use hot water or steam for bottling lines. The added benefit for steam is that it has better penetration because the gas goes places where the hot water can't. So it is very commonly used in bottling lines. I would say hot water is more commonly used, but they're relying on the equipment actually coming up to 185 degrees. Next question: would 11 psi at 99 degrees Celsius be sterile for steam? Yes, that would be sterile. Because now you're dealing with steam, so it's got a higher energy release when it's actually cools down, and that pressure, you'd have to have a specific amount of time. Usually it's 20 minutes, but normally, as the steam is being generated, it's being evolved off, and the microorganisms stay behind if there's any surviving. Okay, I have 2 minutes. Are there any more
We've got
questions?
them all answered, Randy. So right now, I would like to encourage everyone to go take the post-webinar survey. The link is there up at the top of the screen. Also, I would encourage everyone to go visit us on Facebook, as well as visiting the eviticulture.org site. A PDF version of Randy's slides is available there in the file share pod. So if you'd like a copy of that, you can download that. I would also like to thank Randy very much for your talk. It seems like everybody learned a lot of really good information, and thanks to Anna Catherine for being on hand to answer questions once again, and for the others who chimed in to provide information too in the chat pod. It really helps make the webinar a lot more interactive. And thank you, Chris Gurley, too, Anna Catherine says. So anyway, with that, I think we're done. So thanks again, everyone. It was a good time. Okay, thanks,
Okay,
Randy.
everybody have a good day. If you have questions, feel free.